And welcome to EELE 101 Introduction to C Programming. This week we will be using the linear array camera to follow a line. Alright, okay. Okay, so first thing is a warning. So you have your camera board and you have your Freescale Freedom board, and make sure you connect the right signals from the Freedom board to your camera board, because if you get it backwards you can damage the camera board. So make sure that the ground is attached to ground and the analog in is connected to analog in and your voltage to VDD. So the 3.3 voltage is connected to VDD and clock to clock. Otherwise, if you get this backwards, you can damage the board. So here we've shown that ground is connected to the black cable, so we want to make sure that the black side is on the ground of the board and also connects to the ground on the Freedom board. Okay, so just make sure you get this correct. Alright, another thing you should do is unplug your servo cable while you're programming the board. The reason for this is when you plug the USB cable from your computer into the Freedom board and your servo motor is connected and your program starts to run and tries to drive the servo motor, there can be a lot of current that needs to be sourced from the USB on your computer to the servo motor. And your USB connection from your computer is not built to handle that amount of current, because that really should be coming from your battery. So anytime you connect the board to your computer, make sure that your motors are not running, and so you need to unplug the servo motor cable while you're programming it. Okay, and this is just a safeguard for your computer. Okay, so let's look at the camera. The camera is a 128 pixel linear image sensor, so this is a line camera. It's not a two-dimensional camera. There's just 128 pixels in a row, and this is what we will be using to detect a line. Okay, we'll be able to focus this camera, and the minimum integration time is 34 microseconds all the way up to 100 milliseconds, and we'll see why this is important later. And of course the resolution is 128 pixels. Okay, so that camera information will be sent to the Freedom board. Okay, so this is what an example output of what you can see with the camera. Notice here in the image that only a single line is scanned across. Okay, so here we're taking a picture of this bagel, and notice we're only looking at black and white or grayscale values. And so here you can see down here, if it's low, it's dark, so we can see the dark center and the dark edges. And then it's brighter, but it's varying because of the speckles that are in the bagel. So there's 128 pixels across there, and this is an analog output, so we get 0 to 5 volts that tells us how bright the image is at that point, and that's our information. Okay, so we should talk about integration time, and what's happening here is light is hitting the photodiode, so there's 128 of those, and that creates a photocurrent, and that causes charge to be sent to a capacitor. Okay, but the main point here is the charge accumulated at each pixel is proportional to two things. It's the light intensity and the integration time. So the brighter the light, the more charge will be stored as a function time, and then the longer time you integrate, you get more charge into the capacitor, which increases the voltage. Okay, so yeah, there's two things that you can control. Well, you can't really control the light, but you can control the integration time. Okay. All right. So how do we get data out of the camera? Okay, so uh, there's three things here. We have to send a clock there. So notice here we have this clock going. Um, this serial input, here's a pulse that comes along, and this defines the beginning of a sequence where the outputs of each pixel will be sent on the output line. So this is the analog output. All right. So internally, there's some stuff going on. This, you can see up here that this clock is just going along. Every once in a while, this serial input pulse comes along, and then all the analog data comes out. And so each time that that happens, we get 128 values that we have to capture on the Freedom board. All right, so here's an example where this has been put on the scope. Here is that serial input pulse. Okay, here's a bunch of clock values that gets clocked out. Okay, we primarily are going to concern ourselves with this pulse, and notice this is the analog output here. Okay, here it's a dark value, comes up, dark again, a little bit darker, light. So here, in a sense, would be where you could be seeing a line. Now notice that this is a smaller integration time. So if we increase the exposure and integration time here, we can see that we're getting higher voltages because we're waiting a bit longer for each pixel, okay, and collecting more light, and now we can sort of see the notch better. Okay, so you can set this integration time by setting this constant, TFC default line scan exposure time microsecond. Okay, so this is a big, long sort of variable name. Okay, it's actually a defined statement. Okay, so this can be found in your project code in the file tfc-config.h, and this is located under project headers, TFC, and then the file tfc-config.h. So if you double click on that and open it up, and if you go to line 14, you will see this define statement, which is defining, in this case, this exposure time to be 50,000. Okay. If this is set too high, okay, there can be a problem, because if the room is bright, then the camera will saturate, meaning all the pixel data will end up being a value of 255, which means you won't be able to see the notch or the dark part from the line. Okay, and so this most likely will have to be reduced. The values that you can set are anywhere between 33 and 100,000. Okay, so you have a wide range that you can set. So if the room is brighter, and you'll actually know that this is occurring when the car seems to get lost. It's going around a corner and then just runs off the line, and there's a good chance that it's seeing some reflection and it's being blinded. You know, just like you're driving at night and some car comes down with high beams on and you can't see anything else except the bright light. Okay. So the first thing that you'll need to do for demonstrations, and this is demonstration 1, is focusing your camera lens. Okay, so you will need to connect up this serial input line and the analog output line. Okay, and attach those to your oscilloscope, and you are going to use the SI signal as a trigger. So on your scope, select the channel that is connected to the serial input and set that as the trigger. And so each time that comes by, that will trigger the scope, and then you will see all the analog values. Okay, so you'll need to show the TA that you can do this. And what you'll also need is there's a test page on the D2L site that is basically a white piece of paper with a black line down the center. Print that out, and then you can put that in front of the camera, and so you should be able to see that notch. And then what you'll need to do is adjust the camera lens until that notch looks the clearest, and you're looking for sort of sharp edges. I mean, it's not going to be too sharp, but look for the best one you can get as you focus the camera. Okay, so this is going to show that you can see the data coming out of the camera, and you can focus your camera. All right, so the next demonstration is essentially built for you. So what we've done is modified the main.c file, and so go to the D2L site and get the main steer to line.c and replace the main.c with this file. Okay, so what this is going to do is transform the image data to a steering angle that will be sent to the servo motor. Okay, and so demo number 2 is actually to put the car on a line and see if it will follow the line. Okay, so you'll need to recompile your code after you replace it. Okay, make sure your servo motor is unplugged. Program the Code Warrior. Download the program to the Freedom board from Code Warrior. Okay, unplug the cable, and make sure switch 0. So now switch 0 is here. Okay, so this now controls the rear motors. Okay, so if it's on, then the rear motors will run, and if it's off, they won't. So initially turn them off. Okay, now then plug in your servo cable, then plug in your battery. Okay, so that will turn everything on. You'll place the car on the line. Then you will switch this to on. Okay, so now this turns the rear wheels on, and you probably initially want to lift the back wheels off because you will need to adjust potentiometer 0 until those back wheels are running slowly. Okay, right now there's no control on the speed from the computer, so this is manually set, so just have it set to a slow speed where the car will just slowly move along, and what you want to make sure is that it can respond and steer to the line. Alright, so the question is, how is it steering to the line? Okay, so the modified Demo 0 program is the following. Okay, so here again we have this case 0, which is taken from the 2 middle switches. Okay, alright, there's this block that's been added in. Okay, the thing is we're waiting till we see until we're notified that the camera image data is ready, and if that's the case, then one thing we do, and you don't have to worry about this right now, is we actually load up this information through the serial port. So there's actually a MATLAB script on the D2L site that if your computer is set up to capture the serial data through the virtual COM port that goes over the USB line, you can actually capture this data. But you won't have to worry about this because you can actually see this data on the oscilloscope. All right, and then here, this is the main part here, is based on that data, we are going to call this compute steering angle. This returns a value that is sent to servo motor that sets the angle. Okay. Now here, this is where we actually look to see whether we're going to turn off or on the rear motor. Okay, so here we're looking at switch 1. Here, okay, so here, okay, so we're looking at switch 1 here, and if that's true, then we're going to enable the H bridge. Okay, so this is the um, power transistors that control the current to the motors. Okay, and then we can set the pulse width modulation, so the pulses that are going to those power transistors control how long the current is being sent there, and brief little pulses. And this is a function of where that potentiometer 0 is turned. Okay, so this is where you're manually setting the speed, and that information goes to both rear motors. Okay, and that's if it's on. If it's off, then we actually set the values to 0 and disable it, so there's 2 off switches here in a sense. All right, so here's an example of the data that I captured in MATLAB. So this is the reason I have that little script in there that prints it out, and then you can and have that MATLAB value to actually see this happening in real time. Okay, so here's the raw data, and what I end up doing is having this process data, okay, which I'll run through and show you what is being done here, okay, where we do essentially a pattern matching, okay. And so here we can see that even if this notch gets over here, we can still see that there's a peak is occurring. All right, and again on the right side. All right, so what's happening here? Okay, so there's a pattern recognition approach happening. Okay, one of the assumptions we're making is the template is a 0 mean unit vector. Okay, so now we've taken the camera data. We're going to grab chunks that are the same length as the template. We're going to remove the mean of these chunks. We're going to normalize this vector to be unit length. And then we're going to take the inner product between this template and the normalized data and do this as we slide this template all the way across our image data. And where that is maximum, that we'll say, oh, that's where the notch is. Okay. Now, this will fail if there's too much light. So even with this pattern recognition approach, it won't work if all the values are 255, right? So you still will have to adjust the exposure time if things aren't working correctly. Okay. All right, so here's the template. Notice I actually in the code I've just set up a little function that just writes it to an array. So these values here I just got from MATLAB when I uploaded an example image line, and then I just took a short segment that had the notch in it. I just took 18 points here, so I'm just defining that the notch has 18 points, and I create an array that can store the 18 values. We'll get back to what the steering gain means later. All right, okay, so now if we look at the function where we compute steering angle, all right, we now need a local array and some variables that we'll be using. Okay, notch center is just the center index to the notch. Okay, since we're going to look for a maximum, we need to initialize the peak index to be the initial values we want. Okay, and now we go through the line data. Okay, so now we can go from 0 to 128, except, right, we're going to be grabbing segments out of here, so we can't go beyond the end of the array. Okay, so we will just go as far as we can, and then when we grab the array, we won't be running off the end of the buffer. Okay, so let's actually grab the line data. Okay, so here we go in from 0 to end notch, which is 18. Here we are essentially grabbing the data from the line scan image. Okay, notice I here is this outer loop. Okay, so here we're doing it point by point, and J goes from 0 to 18. So we're grabbing a chunk and then moving it over one pixel, grabbing that 18-point chunk, moving it over 1 pixel. That's why we have 2 indexes here. Okay, and we need to compute the mean, so we're actually summing that as we grab it. Okay, we could have a separate loop, but while I'm doing it, I'm starting the mean processing. And then I compute the mean because we've summed it up, and we just divide by the number of points. Okay, so that's the mean of the array, of the segment we grabbed. Okay, all right, so part of our pattern recognition assumption was that these were zero mean vectors, so we need to subtract out the mean. So now let's go through that array again, and for each value we're going to subtract out the mean. Okay, and now we also need to normalize it to be a unit vector, so we need to start computing the length of that vector. Okay, so here we're squaring it and adding it into the sum. Okay, when we do that, so what we're doing here is we're going and summing up the values x squared. Okay, and then we'll take the square root value of that. Okay, all right, so here, once we've summed up all the square values, now we take the square root of that. Okay, and this is the length of it. Okay, so now we need to divide all those values by this denominator value, except in computing, division is expensive. So instead of dividing every element in the array, we'll take the reciprocal. Okay, and first we need to check that this is not 0 because we can't divide by 0. Okay, because if it is 0, then the length is 0. Okay, so we're not going to divide. That's what this else part is here. Okay, and so here we go and we essentially divide everything by the length. Okay, notice here we're actually multiplying by the reciprocal because multiplication's faster. All right, and finally we are going to compare this with the notch value that we have, right? Okay, and we do that over all values of I. So in this case, we are looking for the maximum value and store where that is. Okay, so this is where we find the best match. We note the index where that occurred. Okay, and that's what we need to do, is use this to calculate how much to turn. So if this peak value was 64, right, then we're right on the line. The line is in the center of the array, we're good. But let's say that notch is over to the side. Okay, the further it is away, the more we should turn to the line. Okay, so here we're going to calculate how much to turn, okay, which is proportional to this distance of how far we are off the center. Okay, we have a little bit of a fudge factor here that kind of worked, but the steering gain is essentially, this is what we were seeing up top where this steering gain was set, is you can essentially control how sharp you should turn back to the center. Okay, and then we also need some limits because we don't want to turn so far that the wheels will actually hit the car. So if it's beyond that limit, we just stop at the limit, and then we actually return what that angle should be. So all we're doing here is looking where the line is and computing how steep or how sharp the steering angle should be based on how far off the line we are. And that's what this function is doing. All right, so get this to work, and how you are steering, and ultimately the speed control will be some programming activities that you will need to be doing in the future. So have a great time getting this to work.